So today we're going to be talking about conservation of momentum. Momentum is going to be another vector, and remember, vector means it has a magnitude and a direction, and the direction, especially if we're going in straight lines, is going to be positive and negative, and then the magnitude is the number associated with it. So if you're finding the magnitude of the momentum, you're just solving for how much momentum it has. And remember, since it is a vector, anytime you see something at an angle, make sure that you solve for the components using sine and cosine. Now the next two things, pick a closed system and pick an isolated system. Those don't worry too much about that. Picking a closed system means we're not losing any mass. So for example, if you drop something on the floor and all the pieces get scattered across the floor, we just have to make sure that we calculate the momentum for every little piece. Picking an isolated system means that we don't want any external forces. So if we have friction, conservation of momentum won't work. And if we have some sort of external push or pull, conservation of momentum won't work. Most of the time, it'll be very, very straightforward. So don't worry too much about picking a closed system and picking an isolated system while you're in high school. Momentum is different from inertia. Inertia is directly related to the mass, no matter what the object is doing. Momentum is the mass in motion, so our object has to be moving for there to be momentum. So for example, I've got two pictures of freight trains. The first freight train on the left, the one that's orange, has no momentum because it's not moving. But it still has a lot of inertia because it has a lot of mass. The second freight train, which is more blue, has momentum because it's moving, and it still has inertia because it has mass. It will have more momentum the faster it goes. So if it has a lot of velocity, a very high velocity, then it is going to have a lot of momentum. If it has less velocity, then it will have less momentum. Momentum is conserved. It's one of those things in science that doesn't disappear. So remember what conserved means in science. If we have conservation of mass from chemistry, that means even if we take an object and smash it into pieces, we should have the same amount of mass no matter how tiny the pieces get. We can smash it until it gets down to the molecules, or we could smash it further until it's down to the atoms, but we will still have the same amount of mass no matter how small we smash the pieces. Or we could also have conservation of energy. Energy can transfer between one object and another object, or it can transfer between forms, like between kinetic energy and potential energy. But the total amount of energy before and after should be the same. Just like energy, just like mass, momentum is conserved. So the total momentum before any collision, any happening, will be the same as the total momentum after that collision, so long as we're taking into account all the pieces. So what kinds of collisions do we usually have? There's usually 3 types of collisions that we talk about. And I do have animations on this slide, but I can't figure out how to get them to animate while I'm recording. But if you check out the PowerPoint, you can see all the different kinds of animations. Elastic means we have 2 objects before the collision, and then they bounce off of each other. Inelastic would be the opposite of that. We have two objects before the collision, and rather than bouncing off of each other, they stick together. So they become one object, which means we had to add the masses together, and they'll have the same velocity as each other. A recoil, it's the opposite of a collision, and it's kind of the opposite of the reverse of an inelastic collision. So we'll have one object that splits into one or more pieces. So one example of this might be a cannonball inside a cannon. Before the cannon is fired, the cannonball and the cannon act as one object. After the cannon is fired, the cannonball goes in one direction, and the cannon will recoil in the other direction. This could also be for anything if we drop it and it breaks. So if we drop a plate on the floor and a lot of pieces go all over the floor, that's also similar. So take a look at the corner. Momentum is mass times velocity. We can't use little m for momentum because it's already taken by mass. So we borrow from Greek and Latin, and momentum is actually a little lowercase p. Let's write some equations with this. We know that the before and after have to be equal to each other. So before is going to be the same as after. And then we have before, we have 2 objects. And afterwards, we also have 2 objects. So for our equations, we'll write the momentum of our first object plus the momentum of our second object, the total momentum before the collision, is equal to the momentum of the first object after the collision plus the momentum of the second object after the collision. So what I'm writing above those p's for after the collision is an apostrophe. It's not a square or to the first power or cubed. And usually the way we say it, like if we have p with that mark next to it, we say it as p prime. And all that means is after the collision. So before the collision, there's not an apostrophe next to it. After the collision, we call it p prime. So that's our conservation equation for an elastic collision. For an inelastic collision, we'll have 2 objects before, and then 1 object after. They kind of squash together. So we would have P1 plus P2 equals P of 1 and 2, because now they're one object, prime. And remember, these subscripts are just to label which object or objects we're talking about. So remember, the subscripts are just labels for which object or objects that we're talking about. Another way you can write this is you can write it as separate objects if you want to. That's perfectly fine. Just remember that these separate objects over here will have the same velocity because they're attached to each other. And up here, you would add the masses. For a recoil or an explosion, we have one object, and then it splits into one or more objects, like so. So, we would have P of 1 and 2 before the collision, and then the momentum of 1 plus a momentum of 2 after the collision. And oftentimes this, especially if it's at rest, is 0. So we can also write P1 prime plus P2 prime and have them equal to 0 if it was at rest before the explosion or before they came apart. Now, one thing to notice is that we are not taking into account the direction in this step yet. Momentum is a vector, so it can be positive or negative, but in our equations, we're not taking that into account yet, because sometimes it's hard to tell which way they're going when we set up the equation initially. When we had sum of all the forces, we could more or less easily tell which way all the forces would be going, so we could have positive and negative in our summation equation. But because this is a little bit more difficult, we're going to see the answer and see the direction later rather than putting it in first. And we'll see some examples with that. On this slide, don't freak out. We already have all of the equations that we wrote down before, but we are adding in the momentum as m's and v's, masses and velocities for each object. The biggest part of solving any of these problems, though, is the first equation that we wrote on the last slide. So all of the ones that I have red arrows pointing to. That is the most important step, not necessarily the M's and the V's and memorizing all those. Don't try to memorize things in physics. Physics is one of the amazing sciences that you don't have to memorize things for. I asked you to memorize so far the units of everything that we use and the order of Newton's laws of motion. I haven't really asked you to memorize anything else because you can think your way through a lot of problems in physics. You just have to get used to it. So let's do some examples. The strategy for solving any conservation problem in general is to draw a before and after picture. And if we're doing a conservation of momentum picture, from that picture, or if we're doing a conservation of momentum problem, once we have that picture, we should write a conservation of momentum equation from that picture. So let's see how that would work. If we have a 60-kilogram person standing on a 500-kilogram raft, and then afterwards we have, and I'm going to change this down here from jumping off to the left to jumping to the right. if the person jumps off the raft to the right, what is the velocity of the raft? Now, here's our picture. Before we start solving anything, I want you to make a prediction. Which way should the raft move? Should it move to the right with the person? Should it stay still? Or should it move to the left? Hopefully, from experience or otherwise, you should realize that the raft is going to move to the left when the person jumps off of it. My next question is, will the velocity of the raft be 4 meters per second, the same as the person, be greater than or faster than 4 meters per second, or will it be less than or slower than 4 meters per second? I'm not going to answer that question straight away. We're going to solve first. So before we have the person and the raft, so P1 and 2, I'll call the person object 1 and the raft object 2, and that's going to equal P1 plus P2. Before the person jumps off, we have a hint. It says we are in a still pond, so there's no current pushing the ramp in any direction. So the momentum of the person and the ramp before they jump is 0. After the collision, remember, momentum is mass times velocity. So for the person, we take the mass of 60 kilograms and multiply that times the velocity of 4 meters per second. Let me add primes. So for the momentum of the person will have 240. And technically, let's talk about the units. The units are going to be kilograms times meters per second, because mass should be measured in kilograms and velocity should be measured in meters per second. So the momentum of the person after he jumps off is 240 kilograms times meters per second, and the raft should have 500, which is its mass, times its velocity. And we don't know its velocity yet. We're solving for that. So then we subtract 240 on both sides. And then we divide by 500 on both sides. So the velocity should be negative 0.48 meters per second. Does that match with our prediction? So we notice, hopefully, that it's negative, which means the raft is moving to the left, which is what we predicted. And the person, or the raft, is going slower than the person. This also matches with physics, because with this, the person and the raft will have the same amount of force. Every action has an equal and opposite reaction. So they have the same amount of force pushing between them. And because the raft is so much more massive than the person, it has less velocity when they push off of each other. Okay, so for this example, try to draw your picture, write an equation, and then solve it by yourself before I do it with you. the more you try on your own, even if you get it wrong, even if you get a little stuck, the more you try on the own, the better it is for you and for your understanding. So pause the video, solve it, and then check your answer with me. Okay, so we have two bumper cars in a rear end collision. The 25 kilogram bumper car bumps into the back of the 35 kilogram bumper car. So before the collision, we have two bumper cars. And after the collision, we still have two bumper cars. And in this case, they are moving to the right. And they are still moving to the right even after the collision. So that makes it a little easy for us because we don't need to worry about the direction, whether the velocities are positive or negative. This one's 25 kilograms, this one's 35 kilograms. And it's going 5 meters per second, 1.5 meters per second, and 4.5 meters per second. Okay, so our equation should look something like this. Right? P1 plus P2 equals P1 prime plus P2 prime. So our next step is to start solving. So 25 times 5 is 125. That's the momentum of the first bumper car before the collision. The second bumper car, all we know is its mass, and we'll have to multiply that times its velocity, so plus 35v. After the collision, the momentum of the first bumper car should be 37.5, and the second bumper car should be 157.5. And now we keep solving. So this should be 195 times 125 plus 35v. 35v equals 70. So our initial velocity of the second car would be 2 meters per second. Okay, last example. So this time we have an inelastic collision where two balls of clay collide with each other. And in this one, you want to be careful of your signs because notice one of them has initial velocity going to the left and the other has an initial velocity going to the right. So set up your picture. Draw your before and after picture. Write a before and after momentum, conservation of momentum equation, and then solve it through. And make sure you pause the video and do that before you watch me do it. Because the more you practice, the more you'll get it. Okay. So before the collision, we have a large clay ball and a small clay ball, and they're headed towards each other. After the collision, they collide, and we're not sure which way they're going. So we're going to leave the velocity arrow off of it for now because we don't know which way they're going. Before the collision, we know this one has a mass of 0.75 kilograms, and this one has a mass of 0.25 kilograms. The larger ball was going at 4 meters per second, and the smaller one was going at 3 meters per second, but because it's going to the left, we're going to say that's negative. So the equation should look like P1 plus P2 equals P prime of 1 and 2 together. So we can plug in some numbers. 0.75 times 4 will be 3. So that one has a momentum of 3 before the collision. And the smaller clay ball has a momentum of negative 0.5. And then after the collision, we have their masses added together. So 0.75 plus 0.25 is going to be 1 kilogram times their new velocity. So on the left side of the equation, we add 3 plus negative 0.75, which is 2.25, equals 1 times v is just the velocity. So our velocity is 2.25 meters per second. Which way are they going? From our answer, can we tell? We can tell that they are going to the right because this answer is positive. Okay, that's it for today. Make sure that you do practice on your own. Teachers get all the practice during class, but it's your responsibility to make sure you do some practice on your own at home or at the end of class. And make sure that if you get stuck, you ask for help. Teachers can't read your mind, so make sure you ask.